In this video, we'll move into section 4.3, where we'll discuss the idea of the 5-number summary and what we also call a new display that we call a box plot. But just before we jump in the 4.2 video, we just got cut off just at the very end, about 30 seconds too quickly. So I just want to go back to that, to just come back. What am I trying to emphasize here? The whole idea is that we're trying to see that the mean and the standard deviation, that when you have those two values together, that you have a good sense of, again, what's in the middle and the spread of the data. So why am I showing you this? This, again, we'll come back in 4.4, why I'm showing you two standard deviations, and again, a little bit more about the idea of most data. But what I'm just trying to do here is just trying to give you a little bit of an ability to see that spread, to visualize it. So again, if we're doing comparison, we're talking about test grades, or if we're talking about savings, or any situation that by doing this, it's one thing to understand that standard deviation talks about the idea of the spread of data, but for a lot of students, it helps. It helps in this early stage to be able to attach some numbers. So just one more example, if you were a basketball player and you averaged, let's say 12 points per game, so that's your average, and your standard deviation is 2 points per game, well, doing this idea, that would mean, well, what does your scoring numbers look like? Well, in most games, 2 standard deviations below would take you down to 8 points, to 2 standard deviations above would take you to 16 points, and that gives you the idea what kind of a scorer, what kind of a basketball player with regard to scoring this guy is. Yes, that's his average, but gives you that sense. He's pretty much always in this range. Versus, again, let's just pretend we had a second player, so I'll write standard deviation number 2. This guy also averages 12 points. Again, I'm doing the same thing I did here. We don't have to have the same mean, but just trying to get the idea of the spread. So if a second guy had a standard deviation of 5 points per game, but also averaged 12, we'll go 2 standard deviations below. So subtract 5 twice and you get 2, and then add 5 twice and you'd get 22. So again, just seeing the bigger standard deviation here compared to here should be clear that this person's points, because that's the data in this case, are more spread out, his point totals in each game compared to this person. But now we could really see it. Again, most games, this guy is a little bit more consistent. Always, not always, but most of the time getting you at least 8, but never really giving you more than 16 points. But this person, again, you could say who's the better player here. That doesn't answer it. It's what are you looking for? This guy may be a little more consistent, but this guy is maybe a little more, prone to having a big scoring game, but also might have some very low scoring games as well. So this is nothing about that this guy is better than this. It's purely about the spread. So again, this is an example about basketball and points, but if you're talking about salesmen, same thing. If I average 12 sales per week with a standard deviation of 2 sales, you also average 12 sales with a standard deviation of 5. Well, this is what you're doing per week. You have bad weeks where you only make 2 sales. You have good weeks where you make as many as 22 and you fill in all the in between. But for me, my bad week, I kind of never have fewer than 8 sales, but I also never really do better than 16 sales, and I'm in between. So again, standard deviation doesn't have any sense of better or worse. It's just connecting with the mean to try and give us the picture of the spread. Okay, so now we're formally starting 4.3, and we're getting more of that same spread. This idea of a 5-number summary, well, I just talked about having the mean and standard deviation, and with those two data values, those two values, they're not data values, but with those two values, how you can get a picture of all the data, and that's what this is trying to do. The 5-number summary is just going to be a report of 5 numbers, but in just a moment, we'll see how we can then take those 5 numbers and make it into this box plot display. So just one more display that we're going to see. But what are the 5 numbers we're going to look for? We're going to look for, well, first thing, all this, everything here is numerical data, and we're going to have to be clear here that our data must be ordered. Again, small to big, big to small. This is a situation most people would definitely go from low to high because the first data value they find is the low. The second, we're going to get these Q1, Q2, and Q3. And then last will be the high data value. Those are the 5 data values. The lowest value, the highest value, and then in between, these are what we call the quartiles. The first quartile, quartile, and that's abbreviated capital Q subscript 1. The second quartile, capital Q subscript 2, and then the third quartile. These got mentioned at the end of 4.2. If you're reading in the book, they come up here. And again, I'll come back and talk about how these connect to the IQR, the Interquartile Range, in just a moment. But first things, what are these values? Now we'll finally see what these are. And they're really not bad. The second quartile is the data value that cuts the data in half. Does that sound familiar? It should. If the data value that cuts the data in half, that's the same thing as the middle data value. We already know that. The second quartile is the same thing as the median. That middle data value. So once you identify that middle data value, every data value below goes into the lower data set and everything above goes into the upper data set. So that's kind of what we're going to see here. I'm going to try and draw this out a little bit. So we've kind of already established the low and the high come up pretty quickly. You've got all your data in order. So now you identify this middle. So that's your Q2. So now everything less than that, that's the lower data set. And everything bigger is the upper. So half the data values below, half the data values above. Now, and this is the order, everybody. I know we're looking for these 5 numbers, and most people, again, once you have this data in order, the low and the high, well, that's the first and that's the last data value. So they're very quickly identified. Again, as long as you have your data in order, then you would get this middle data value. And now, Q1, the first quartile, is the data value that cuts the lower set in half. In essence, it's the median, but not the median of everything, just the median of the lower data set. And then similarly for Q3, that will be the data value that cuts the upper half. It's the Q3 would be somewhere up here, and that would be the middle data value of this upper data set. So this is the picture, everybody. And now we're certainly going to do some examples in just a few moments, but this becomes the box plot. What you would do, this is numerical data, so we'd start off with an x-axis. So our numbers, and again, we'd cut to what we care about. So do we care about numbers in the tens, the hundreds, whatever. So just, we'd have some numbers here. And then we'd identify these 5 values. And when you do this, here's the first thing, everybody. When we draw a picture, our first thing that the brain tries to do is to keep this sense of proportion. So we just draw these 5 values just like I did here. And it's like almost equal spacing. Space, 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 but they're all kind of equally spaced. But when we actually find these numerical values, they're not always going to be equally spaced apart. So let me just make up some numbers for this first one. Let's pretend the low value is 8, the Q1 is 10, Q2 Q2 is 20, Q3 is 22, and the high would be 45. If those were our 5 numbers, well, let me get some scale on here. So I'll go 0, 10, 20, 30, 40, 50. And my scale on the actual x-axis, I'm trying to be consistent. But now I don't just put these 5 values, I don't just mark them off randomly. I put them where they go in relation to these numbers. So 8 would be a little bit less than 10. There's my low. 10 is Q1. That would go right here. Q2, 20, would go right here. Q3 is only 22. So that's just a little bit bigger than 20. And then 45 would be up here. Now, you'll notice the second thing. First thing you just notice, why am I making these different length lines? I'll come back to that in a second. But just to notice, those are the 5 numbers. They're according to this scale down here. I don't just mark off 1, 2, 3, 4, 5, where like I was saying, we don't just put equal spacing. We put these data values where they go here. Let the scale on the x-axis determine the spacing between these lines. Now, why do they call this a box plot? You make these 3 lines in the middle. These 3 longer lines represent Q1, Q2, and Q3, and they always go in that order. You make them the same length, and you make this box around them so that the Q1 line represents the left side of the box, the Q3 line represents the right side, and Q2. Notice, it doesn't have to be right in the middle, but it's just a vertical line somewhere in the middle of this box. And then you have a horizontal line that cuts through the middle of the box and goes to the extreme ends. And just this little, I've actually seen some where they just put a point on the end, but what I was always taught before, and what a lot of other books, just this little like half line. So we're not trying to make it too crazy here, but the Q1, Q2, Q3 lines are definitely longer than the low and the high data value lines. That is what a box plot looks like. Now, it's still a display. We'd still have to label. We wouldn't label this x-axis. We'd try and label, what is this? Are these salaries? Are these numbers of text messages? Is this how long it takes you to complete a puzzle? Always all that, everything we've always said about displays and graphs, keeping everything well labeled. So that's how we make a box plot. But again, it's all about having these numbers first and then putting it on your x-axis in this form. In a few moments, we'll see we could do comparative box plots. Maybe we're comparing, what is this? This, for an example, let's again say this is the time it took to complete a crossword puzzle. And this is in minutes. So maybe we're looking at 2 different groups of people. So this is group A, this is their box plot, which shows their 5-number summary. And then we could above or below have another box plot to have a little bit of a comparison. But how we need to understand this, because it's very common that people misunderstand, because again, our brain already has a lot of things it looks for with ideas to space and size. So the real understanding here, why do these 5 numbers give us a good summary of the data? Because everything is cut into these equal pieces so that 25% of the data falls between these 2 values, right? Go back to here. The second quartile, the median, is that middle marker. It cuts the data in half. 50% of the data below, 50% of the data above. But then Q1 does that same thing, but just in this lower data set. So that means 25% of your data comes between the low value in Q1. Then you get another 25% between the first quartile and the second. Then you get another 25% between Q2 and Q3. And then you get the last 25%. Right? This has to add up to 100%. We need all the data values to be represented. and that's the proportion. But again, this is where people get confused. We see these equal percentages, so we want to draw them equally spaced. Sorry, pardon me. But the data we collect, sometimes it may be that nice that these things are fairly equally spaced, but they don't have to be. So looking at this example, 25% of the people who completed, let's not call it a crossword, that would be a pretty quick time. So just whatever this puzzle is, here to here, that is a very small gap. So in a lot of people's minds, this represents a small number of data or a small number of people, whatever the context is. And then jump out here, people see this bigger gap and they go, oh, there's lots of people out here. That's not it at all. 25, all the people who completed this puzzle, 25% of them completed that puzzle between 8 and 10 minutes. And then we got another 25% of the people completed the puzzle between 10 and 20 minutes. And then another 25% between 20 and 22 minutes. And then another 25% between 22 and 45 minutes. So this is a bigger interval, but it still represents the same number, the same proportion of people. So that's one of the first things to get used to. It's easy, again, to first thing just see, okay, we'll get practice getting these numbers in just a moment and then go into our box and whisker plot. But, you know, and again, at the very end of this, we'll do a little bit more just discussion. We're getting a good bit through chapter 4 and people are seeing the numerical part that they almost feel like has been missing. But don't forget, there's still writing, there's still understanding, there's still choices to be made. There's still decisions, you know, who was better? What would you prefer? And again, even though these may not be universal decisions, they may have your own unique perspective on them, but they could still help you make that decision what's best for yourself. So, that's the way to understand this. And that's why this gives us a full spread of the data. With the mean and standard deviation, we can get a picture of where most of the data lies, just in that generic 2 standard deviations below to above the mean. Here, it's even more precise, because not only do we just see, okay, the times go between 8 and 45 minutes, we get these extra numbers to feel and see lots of people in this tight little window, lots of people in this tight little window, and then the same number of people spread out over this much larger window. Okay, so we'll still get more practice with that as we go along, but now let's get back to finding these numbers. So what I'm going to do, we're going to want to see, you know, plenty of good examples. So what I want to start with, let's go back to this example we had in 4.2. We were looking at students competing in their broad jump, and we had 10 students. So let's just get that data value. Broad jump in inches. I'm already going to put the data in order. And this, if you want to put it in a column or in a row, this doesn't matter. I kind of expressed when I'm using these formulas, I kind of prefer columns. Just for a lot of people, sometimes some of this has to do with the Excel program that we'll still try and get to a little bit. We won't use it for much, but to at least show you some basics. Some of that practice comes from people who use Excel, but it could work either way. I can't exactly say why, but now when people are trying to put these data values in order, more people tend to go in a row. So putting them in order, 16, 21, 22, 24, 24, 30, 32, 34, 44, 51. We had 10 students. Again, just to remind you, this came from 4.2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There they were originally. I put them in order going down here, and I just took that same order and put them across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So with this setup, let's find the 5-number summary and make the corresponding box plot. Oh, one very quick thing to note. Our book calls it a box plot. Older textbooks tend to call them box and whiskers. And those are the books that always put this extra little piece here. And that was kind of the idea, especially because like we said here, a lot of our data is a little bit more distributed so that you end up with something. I'm trying not to make this perfectly symmetrical, but something a little bit more symmetrical, not quite as bunched. Little gap here, bigger here and here, but something more like this. And the idea was it kind of looks like this is the middle of a face and here's the whiskers coming off on the side. It's a little silly, I admit it, but just so you've heard that expression. Again, our book really calls it a box plot, but just in case I accidentally say box and whiskers, it's the same thing. So let's go through, find the 5-number summary. The low value is 16. And again, just good habits, always these values, always keeping our units included. When you're asked to identify, always, again, these little habits. It's easy to forget, but always keep them. Q1, Q2, Q3, and the high is 51 inches. But now, just like we showed when I was actually just defining them, you have to find Q2 next. That has to be the order. You have to find Q2, so therefore you can establish the upper and lower halves, and then you could find Q1 and Q3. So starting with Q2, well, I have 10 data values. So 10 plus 1 divided by 2. This is the slightly goofy case where the median is actually the average of the 2 middle values. So 1, 2, 3, 4, 5, and 6. Or again, it's other direction too. But now we're starting to get into a situation where, again, the quartiles, if you're just finding the median, doesn't matter if you go low to high or high to low. But now when you're finding these others, now you're assumed that Q1 is the lower data half. So why don't we just always put the lower data half on the left side? Again, that's the natural way we write numbers anyway. So we average these together. So 24 plus 30 divided by 2. And we get 27 inches. Now, we've already seen how finding the median has these little cases based on whether you have even and odd numbers. Now, seeing this separation into the upper and lower data half, again, just need to see the little few different possibilities. We didn't have one middle value here. So we found this as the middle value, as the average of these two. And now that value, this new value that wasn't in the original list, that is the divider. So that the 24 and the 30, both of these were used to get the 27, but neither one of them is the median. So this one actually goes into the lower data half, and this one goes into the upper data half. And now we start again, and now we're just looking at these. Now there's only 5 values here. So 5 plus 1 divided by 2, that works out cleanly. So we just get one nice first quartile, one value here. And now we'll come to the upper half, same thing. There are 5 values below, there's 5 values above. So 5 plus 1 divided by 2, we go to the third. And the third quartile would be someone who jumped 34 inches. There is your 5-number summary. Now again, I'll keep coming back. We want to see the different cases. Maybe it's Q2 has the 2 middle, and then Q1 and Q3 get 1. Maybe this only has 1 value, and then we have to do the middle 2 on both of these. Maybe this has the middle 2, and both of these have the middle 2. Maybe all 3 are just 1 value. Every possibility comes up here. So that's just the first example. But while I'm here, before I keep going, let me go right into the box plot. Found the 5 values. So looking at these, let me get a decent scale. Broad jump, measured in inches. Again, I don't have to start at 0 here if the first value is 16. And these are the little things. You set your scale. So a lot of us like 10s, 5s, things of that nature. So it's perfectly fine to start here at 15, and I'll go by 5s. 20, 25, 30, 35, 40, 45, and 50. 16 just above the 15, little dash. 51 just above the 50, little dash. Some people like this middle line before they go too far here. And then the bigger lines for Q1, Q2, Q3. Q1, about here. Q2, 27, would be about here. Q3, 34, would be up here. And there's the box. And like we said, I didn't just make a box with equal, pieces on each side. I didn't just draw this line down the middle. This is shorter, this is longer because of the scale. That's just all there is to it. And now that we've got it, again, same thing. If we never saw this information and maybe we had 100 students, well, 25 of them had their broad jump between 15 and 22 inches. 25 of them had a jump between 22 and 27 inches. 25 of them between 27 and 34 inches. And 25 of them between 34 and 51 inches. That's how we would understand this. But now, little tweaks. Let's see those other little possibilities. All this was set up with that original data set, and this was all correct, but now I'm going to change color here. I'm going to add one new value. Let's say we had one more student, and they jumped 53 inches. Just so I can keep this in order, I'll just add one more really high jumper, one very far jumper. Now, low, still 16. High would now be 53. But now look at the different possibilities. It's not possibilities. Look at what happens now when we go to find the median. Now with this extra value, now I have 11 data values. So now I get a clean middle value. Not a middle two values, just one middle value. 1, 2, 3, 4, 5, 6. 30 inches would now be the second quartile. And this is the biggest one for everybody to get used to. Because in the first example, when Q2 is the combination, you get that combined value, but then the value that was below it goes into the lower half. The value that was above it goes into the upper half. But now that you actually have one middle value, that value is used. This is still the lower half, and this is now the upper half. So we got the 30 as the median, the one value. So now everything less than that, we actually use that, so just everything less than that. Here we introduced the 27 and everything less than that, which included the 24 that was used to get the 27. But here we just had that value, so everything less. Now, still 5 values below. 22 is the middle, so that one works out. Coincidence, everybody. I'm not trying to say that's how it would always work. If I put a new lower value in here or another middle one, it's just trying to get us used to how we figure these spots out, seeing the different cases. And now up here, we'd have a new third quartile, which would be 44 inches. Now we're looking at these 5 as the upper, and still the same 5 plus 1 divided by 2. That gives me the middle value. One more change. This may start to get a little bit messier still. Let me try and use a pencil. So we added a 53, and now let's also add in a 54. Now we have 12 total. So now we would get 6.5. So now we're getting a middle 2 again, but now it's the 6th and the 7th middle values. I'm just focusing on the quartiles, everybody. Notice this little change. I'm not making a whole new box plot. I just wanted to focus on, again, the little differences in finding the median based on how many total values, only having one middle, having 2, and then how to break up and distribute the rest of the set. We're back to a middle 2. 1, 2, 3, 4, 5, 6, and 7. These are the middle 2. We'd average those. 31 would now be the second quartile. And now once again, we had a middle 2. So that is now your middle line. 30 and the values below are the lower data half. 32 and the values above are the upper data half. And now again, this is all just coincidence. It's just what happens. We deal with it no matter what. Now the middle was a nice 1 value, but now when I look at the lower half and the upper half, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Now we're back into the even case, where we've got to do the average of the third and fourth values. So now 1, 2, 3, and 4, we'd get the first quartile would be the average of those two, which would be 23. And then 1, 2, 3, and 4. The third quartile would be the average of these two. What was that, 6, 7? So we'd have 47.5. We'd average those two together, 44 plus 51 divided by 2, and get 47.5. So again, if you've been pretty good with the median up until now, this isn't bad. But for some students, just that little bit of hesitancy, just to remember to go back, you're definitely going to need to be clear. It's not going to give you the nicest case. Plenty of people are like, well, it could happen that all three of these are just one value, but you need to be prepared for any of those different possibilities. Okay, so where do we go from here? That pretty much covers everything. But what I would like to do, I'd like to finish this section just now making a few more box plots, but now we've already concentrated on how to put it together. Let's focus on trying to interpret it, getting back, being able to say just a little bit more, and then at the very end of this video, I want to go back and mention the IQR, the Interquartile Range. No test problems from there, but I just want to make it clear. I mentioned that quickly in 4.2, but you didn't even know what the quartiles were at that point. So now that you do know that, just to make it clear how those would be used and how that defines an outlier. So, again, we are given the box plots now. We are given the box plot that shows how many, let's do a production example. What are we gonna make? I'm just gonna make something up. We make doodads. How many doodads each employee made on the manufacturing line? So I'm giving you, and we're gonna do this by shifts. So we're going to have two box plots. We're going to compare the first shift to the second shift. So we have number of doodads, labeling our axis, not just an x-axis, making it clear what this represents. And now I'm going to have two boxes. So I'm going to make it clear. This first one represents shift 1, the day shift, and the second one is shift 2, the night shift. So number of doodads. Let's go 10. Actually, let's jump a little further. Let's make more doodads. 30, 40, 50, 60. There are a number of doodads. And now for shift 1. And then for shift 2, so before we do any kind of comparison, let's just quickly take a look and see, what it is that we're seeing here. Shift 1, the slowest employee, the person who made the fewest doodads, made just more than 40, maybe like 41, 42 doodads in his last shift. And then 25% of the employees made between, what is that about? So 41 to about 59. Then another 25% of your employees made about 59 to maybe about 64. and then another 25% made between 64 and 72, and then another 25% of your employees made about 72 to about, what is that, maybe 77. But now look at shift 2. Remember, everybody, what I'm telling you now, this is kind of like just reading a regular frequency table. We should all be able to get that understanding. I want to, again, really illustrate that. That's not speculation. That's just literally reading what the chart tells you. So now in shift 2, well, we've got some employees that make as few as 30 doodads, and 25% make between about 30 and 42. Maybe that's about 43. And then 25% make between 43 and maybe that's about 53 doodads. Then another 25% make between 53 and maybe about 79 doodads. And then we still have another 25% of the employees that make between 79 and 91 doodads. So, what would you say about the performance of each shift? How could you compare? And now, there may be some situations where it is very clear that one shift or one group or one employee section, whatever it happens to be, is clearly better than the other. But most are something like this. There's middle ground and it's perspective. If you wanted to argue that shift 1 is the better shift, what would be the basis of your argument? You'd probably be focusing on these two pieces. That in shift 1, the lowest, I don't want to say worst exactly, but the slowest employee made 42 doodads. In shift 2, you had 25% of your employees made, again, this was a tiny bit more, but below 43 doodads. Your worst employee compared to your worst 25% of your employees are producing, these people are producing worse than this one person. So that's something you could focus on. That would be a positive for shift 1. The other thing might be up here. Look at the consistency of these people. You do have 25% of your workers down here, but all of these people are doing better than all of these people from shift 2, but focusing on the top end of the spectrum. The consistency. 25% of your people are getting about 60 to 64, another 25% between 64 and 72, and then another 25% between 72 and 77. So you're literally looking at 75% from here to here. That's 75% of the employees are making at least, 59 doodads. Whereas up here, well, what would you focus on that's good? You'd probably focus more on this part, that all of these people are making more, that's 25% here, they're making more doodads than every single person down here. So this is just a common situation. What's better, what's worse, it's a matter of perspective. But what can you see? Maybe here you want to talk a little bit more about the consistency. A really large percentage of your employees in a similar ballpark as far as their production is concerned, and overall comparing, it's a good production spot, right? This is a good ballpark. All these people are doing better than all of these people. But on the other side of that, maybe you focus on shift 2, and you could pick on these people as being, the worst workers that kind of hold shift 2 down, but then you have these people that are so super good. So it's kind of like the extremes. It's kind of like what we were doing with the standard deviation at the beginning of this. You may have some similarities in the middle, but what about the extremes? These people are a little more consistent. These people are a little more spread out. Okay, let's change it. Same 2 box plots, but now let's talk about, let's say this represents the yearly salary in thousands of dollars. So this 30 would represent a salary of $30,000 per year, $60,000 per year, and so on. Very, very quickly, I want to point out a few quick things. Take advantage now that we're talking about salaries. One quick thing just to point out, this is another good example. If you think about the United States and you think about what is the average salary, this is another situation where the median was a more appropriate value than the mean. Because, you may see this in the news, you may not, but the disparity of wealth in this country, that when you have, the median salary is, I forget the exact number, but it was over $60,000. So that's a pretty good yearly salary. Now, when you live in New York City or Washington, D.C., some of the more expensive areas, that still could be tough to live on. But when you get to other areas, $60,000 is a very, very healthy salary. I don't want to go too deep into this, but there's a lot of old little metrics talking about how much money should you spend on rent or mortgage. And, in New York City, a lot of us spend like half of our money on rent or mortgage. Other places don't quite spend that much. They suggest more like a quarter or a third. But that's just some quick information. But if that is the median, why is that more appropriate? Well, in the United States, if you want to compute the mean, you have to keep all those billionaires in mind. Think about all the zeros in $1 billion. I mean, even right here, that's 1 million. That is $1 billion. Okay? That is a huge, huge number. So when you have people making hundreds of millions or billions, and then you start mixing them in with people making tens of thousands, again, that's going to really skew the mean to make it look like it's much, much higher, but it's because of these people pushing that number. So that's one very quick thing. That's just for your information, just to realize that if you ever do look into average salary, it's more common when they talk about the country or a state that they report the median, and that's actually a good thing. That's actually a better representation of what's common or average. The second thing is that I also realize that a lot of students at this point, you're not so familiar with the correspondence between hourly rate and yearly salary. So just really quickly to point out some quick numbers. If you make $10 per hour, if you work 40 hours a week, that would give you $400 a week, 52 weeks a year, but just call it 50. And very, very roughly, $10 per hour is approximately about $20,000 per year. So just to help you go back and forth a little bit. And you could just keep going with this. So if it's $20 an hour, you double this, well, that would double this. And you get $40,000 per year. If you make $30 an hour, that would be $60,000 per year. So I just wanted that for your information. Just sometimes we had a test where we used hourly rate. Other times we talk about yearly salary. I just want you to be familiar just going back and forth with that. Okay, so now pretend this is yearly salary. And these are two different companies. So let's call this box plot goes for company A, and this second one goes for company B. What company do you want to work for? If you're looking at salaries, what's good, what's bad? Well, again, it's still very, very similar. If you choose company B, why would you want to choose company B? Well, you may point out that you have this chance to make more money than any person at company A. But then again, if you're in company B, you have employees here that make less money than any single employee at company A. So again, it kind of comes back to this is more spread out, this is more consistent. So what do you prefer? Well, maybe people talk about, look at this, again, 75% of your employees are making between $59,000 and $77,000 per year. So you're pretty much getting everybody in that, just below the national median to a good little bit above. And that's a big chunk of your employees. Still 25% of them make less than that, but still not bad, consistent. So why would you pick here? You may talk about that, with a little bit of time, I can get to this, and this is a good salary range. And so many of their employees are making this salary range. But if you come here, yeah, you've got the possibility to be on the top, but you also have the possibility to be on the bottom. And with these two sections being lower than this, That's 50% of your employees are making less than about, I don't know, $52,000, $53,000 per year. So half make below, half make above. You still have these people that make more than any employee in company A. These people make less, but overall, 50% of your employees make less than this, whereas 75% of your employees in company A make more than this. You just see, we can keep going back and forth, keep going round and round. There is no answer of what is better, what is worse. I mean, if every employee in company B made more than every employee in company A, we could say salary-wise, that's definitely the better option. But maybe there's still other factors we want to consider. But still, there's so few times that just one piece of information gives a absolute clear cut, this is definitely what you need to do. We need to, again, be able to discuss the different possibilities. But the big thing from this section, being able to find the 5 numbers to then make the appropriate box plot. That's without a doubt the big thing to get started with. But then secondly, getting more comfortable looking at these. The book has several other examples. There was one good one where they had different NBA teams comparing the salaries of what they pay their players. Again, several other good ones. Make sure you're also looking to see how to do comparisons. Again, always just thinking, what can I say? And always, if you're unsure, knowing, just ask. If you're unsure, is this enough? Should I say more? All you have to do is just ask. Okay, just about finished. The very, very last thing. Just going back to that idea of the interquartile range. What they do to figure out the interquartile range is simply this. Q3 minus Q1. That gives you this interval. So in this case, go back to the 34 and 22. 34 minus 22 would be 12. So the interquartile range would be 12 inches in this case. Why is that important? Like I said, folks, we're not going to do anything. I'm not going to ask you to calculate the interquartile range. I'm just trying to make this a little clear because now in 4.3, now that they have that, they talk about any data value. How do you define an outlier? This is on page 169 at the bottom. An observation, a data value that is more than 1.5 IQR away from the edge is an outlier. If it's more than 3 IQR, it is an extreme outlier. So they even classify. So just quickly, again, I don't want to go crazy with this, but just in this situation, the original, before I added these extra data values at the end, just the original situation we had, 34 minus 22 gave us 12 inches for the IQR. 12 times 1.5 is 18. Any data value that's 18 inches above this one or 18 inches below this one would be considered an outlier, okay? And then take that further. So again, the IQR was 12. Multiply that by 3 and you get 36 inches. Now this doesn't even make sense on the lower side. These are jumps. You can't have negative jumps. But the big picture would be if you could go 36 inches below this or 36 inches above this, data values found below that one or above that one. Again, not this. Below the 36 inches less than this or above the 36 inches more than this, so that would be 70 inches. If someone jumped more than 70 inches here, that would be an extreme outlier. 18 inches more than this would give you 52. So jumping more than 52 inches would be a regular outlier, and more than 70 inches would be an extreme outlier. So that's it. Again, I'm not worried about the formal definition of an outlier. We should be familiar, but that is how you would formally classify. Not just seeing a value that's kind of high or kind of low compared to the rest. A formal way to define it, that is an outlier.